Hi, and welcome to part 2 of chapter 5. We're talking about the probability rules. Like what is an event? Why would something be mutually exclusive or disjointed? What are our addition rules? What does the U mean? What does the upside down U mean? And all of those things. That's what we're going to cover in this particular video. So, here are the things, here are your learning objectives, what you should be able to do, not necessarily by the end of this video, but by the end of our in-class day regarding this, and we'll go over some questions in class. So can you describe a probability model for chance process? So this is going to be different than our simulation model, and so we'll learn a little bit on how to create a probability model using basic probability rules. We'll understand what the complement rule is versus the addition rule. We're going to have a visual representation of both of those as well. We will learn how to use and more than likely interpret two-way tables and Venn diagrams to model chance process. We'll be able to calculate probability involving two events. And again, usually that's from a two-way table or a Venn diagram. And we'll use the general addition rule to calculate probability. So again, this is a little bit more of our math portion. It's not crazy math, but it is probabilities math. So let's dive on in. In our previous video, in our previous day in class, we did simulations where we stated, planned, did, and then concluded. But you don't always have to rely on those simulations. You can see that they're kind of a lengthy process to set up. And so you can actually do a probability model. But in order to do that, you need two different parts. You need the sample space, and it's just a fancy word for your actual possible outcomes, and then your probability model itself. And that's typically we represent it as like P of whatever. And so that P is your probability model, the probability of each outcome, and then that sample space would be that of whatever. Okay, so if I roll two dice, two six-sided die, how many different possibilities are there? And so this is kind of how you begin building a probability model. And so here I have all 36 possible different combinations of rolling two different die, two different six-sided die. So you could get a 1 and a 1, a 2 and a 1. You could get a 4 and a 4, or a 3 and a 5, et cetera, et cetera, et cetera. So here's all 36 possible outcomes. And so this is what we call our sample space, is that there are 36 possible outcomes. It's not necessarily that you're dealing with all 36 outcomes, but there are 36 of them. So since the dice is fair, they're the same size, same opportunity, et cetera, et cetera. Each outcome is equally as likely. So your current probability is 1 out of 36. So what's the chance of rolling any outcome would be 1 out of 36. You guys understand that? That's kind of basic probability math. But let's move on. What if I don't just want to know what is the probability of rolling any combination of two dice? What if I want to know a specific combination? And so that's what we're going to kind of walk into. So a vocab definition here is an event, collection of outcomes for some chance process. We typically designate these as capital letters, so you might see it as P of A, P of B. And in this particular instance, I think we're about to do an event where what would be the outcome where both of my die add up to or sum to the number 5. So that would be a 2 and a 3, a 4 and a 1, et cetera, et cetera. So we're going to write that event as A. So the sum of 5 is event label A. And here we go. We have a 1 and a 4, a 2 and a 3, a 3 and a 2, and a 4 and a 1. And that's just because, you have the opportunity to roll a 1 or a 4 on one die, and then et cetera. So you have kind of the similar outcomes, but different. Anyway, so there are 4 outcomes that result in this sum of 5. And so then our new probability P of A, this particular event would be 4 out of 36. So that's what we're talking about when we talk about those events. Suppose event B is defined as sum is not 5. So that would be all of the remaining other probabilities. We're actually going to learn what this vocab is when we're talking about the events outside of it, or the probability outside of an event. We actually call this a complement, and we'll learn that vocab word in just a little bit. But what would be the sum is not 5? And if you just said, okay, well, what's 36 minus 4? You're on the right path. It would be 32 over 36. But the reality of it is you can also do 1 minus 4 over 36, and that is another definition, and that would be our addition rule. It's called the complement rule, and that's where you take 1 minus the probability of the event that you're not supposed to be associating with. And so that's where that 36 minus 4 technically comes from, because when you subtract fractions, 1 minus 4 over 36 becomes 36 over 36 minus 4 over 36. So that's where the math comes from behind that. But here's some basic rules of probability. I'll go over each, but we'll also see the like kind of mathematical definition or formulas on the next slide. So the probability of any event is a number between 0 and 1. You guys know this because you talk in terms of fractions. So those would be numbers between 0 and 1. A probability of 0 means it cannot occur. And so all possible outcomes together must have probabilities whose sum is exactly 1. So if I have the probability of event A and the probability of event B and the probability of event C, if they're all dealing with the same outcome set, then they all have to sum together to be 1. If all outcomes in the sample space are equally likely, so somehow the probability of getting sums of 1s and 2s and 3s and 4s and 5s, when we're talking about the dice example, were all the same. Somehow they were all the same. Then this is bullet point 3 we're talking about. You would have this formula where the number of outcomes corresponding to event A is divided by the total number of outcomes in the sample space. So that makes sense, right? If event A and event B and event C all have the same number of outcomes, then couldn't we just write it as this formula? Yes. So it's just kind of a common sense thing, but we'll mention it. And then the bullet point 4 and bullet point 5 are dealing with our two main vocab concepts from here, and that would be the complement and the mutually exclusive. So bullet point 4, the probability that an event does not occur is 1 minus the probability that the event does occur. That's a fancy way to say what we just did. When we found the probability of what wasn't a sum of 5, we took 1 minus event A. It's as simple as that, and that's called a complement. If two events have no outcomes in common, the probability that one or the other occurs is the sum of their individual probabilities. So if we have two events that are mutually exclusive, they cannot share properties. I couldn't do a Venn diagram and have the overlap. My Venn diagrams would be separate. So this would be a mutually exclusive. We also call this a disjoint. So these are vocab words you may see on the AP exam, and so I'm just stressing those words that if they're talking about this is what they're talking about. Probability two-way tables, Venn diagrams, and mutually exclusive or independent events. So if two events have no outcomes in common, then the probability that one or the other occurs is the sum of their individual probabilities. Can be rewritten as simply, P of event A plus P of event B. That's basically what that's saying, and it's going to equal, 0. So here they have that again, that, if they are mutually exclusive, they are disjointed, then your probability in the end must be 0, because the probability that they would occur together would be 0 because they are mutually exclusive. So let's see those same concepts summed up in actual notation form, in our symbolic form. So here it's saying that all probabilities occur between 0 and 1. That's what we just talked about. The sample space in a probability must be equal to 1. What a concept. All probabilities all together for that particular outcome have to eventually be 1. Okay, well, this is what they're saying. P of S is equal to 1. In the case of equally likely outcomes, here's that formula again. And finally, we get down to the two main things, the complement rule and the addition rule for mutually exclusive. And here you can see, here's that complement rule, 1 minus the event I'm excluding. And then here we have our mutually exclusive, that, if this can't deal with B and this can't deal with A, then, if we add them together, we're going to get to that 0 point. So let's actually do an example together. When finding probabilities involving two events, a two-way table can display the sample space in a way that makes probability calculations easier. Consider the example on page 309. And so this example has to do with the who has pierced ears. And so I've got a little image of it. If you're looking for it in your textbook, I'll watch it. It's this little guy right here. And so we're on page 309, but I've got all the information right here. You don't really need to go to the textbook unless you want to. So suppose we choose a student at random. Find the probability that the student A has pierced ears, so there's question 1. B is a male with pierced ears, question 2. And C is a male or has pierced ears. So there's that very important C part where we're going to do an or concept, and that's where I think kids might make their most mistakes. A and B make a little bit of common sense to you guys, but C might be a little bit tougher. So A, if I have pierced ears. So here we go. I go to my two-way table and I see under pierced ears that I'm looking at this category right here. Yes. Does it say anything about gender? No. So I don't care that 19 males had pierced ears or 84 females had pierced ears. I really care about this number, 103. But what is my total number? Am I dealing with 90? Again, no, we're not dealing with a specific male or female. We're talking about all of them together. So it's going to be 103 out of 178. Pretty easy, right? And so this would be and we defined our events as A is male and B has pierced ears. Just a quick note, if it was clearly defined, like let's say I was doing a free response question on the AP exam. If it was a clearly defined event, you could write, like if in the question itself it said A is defined as male and B is defined as pierced ears, in your answer, you could write P of B is equal to 103 over 178. But if B wasn't clearly defined, either you have to define it, B has pierced ears. Look at that. We defined our events right here. And if you don't define it, then this is another thing you could write. So you can literally write the, what do they call it, the vocab or the wordage or however you want to call it. There's a specific word. Hold on. Me. Nope. I lost it. Yeah, I lost it. I don't remember where I read that. But you can write P of pierced ears, and that would be acceptable as well. That would be a definition. That would be descriptive enough to get your full credit on that particular portion of the exam. So let's move on to if I am a male with pierced ears. So now we're looking at a very specific portion. We're looking at male. And we're looking at, yes, I have a pierced ear. So we're actually looking at this value right here, 19. But what is our probability? Are we looking at just the males? Are we looking at the total value? And so this is where I think some kids might struggle a little bit. You might put 19 out of 90. But remember, your original probability, it says, suppose we choose a student at random. It doesn't say choose a male student. It just wants to know that the probability of that student. So who's that student? A student out of the entire 178. The probability that that particular student is male with a pierced ear is 19 out of 178. So don't get lost in your own thoughts. Always reference the language that they have used so you don't accidentally put 19 out of 90. And so moving forward. Before we actually move on to C, I want you to see that they have written, we want to find P, male and pierced ears, acceptable, or P, A, and B, acceptable if the events were defined. So this is two ways that you can write it. And then here is our actual answer, 19 out of 78, and it's referencing P of A and B. And finally, C, if it is a male and has pierced ears. So this is the one that I thought we might struggle with the most, so I went ahead and showcased the answer. But we want to find male or, sorry, it's an or statement. And so we're not going to write and right here. We're going to write or. But in order to do the or, we have to be very cognizant of not repeating values. So I don't want to do 19 plus 84 plus 19 plus 71. And where did I get those numbers? I don't want to do 103 because I'm looking for somebody who has pierced ears, and 90 because I'm looking for somebody that's male. Those are the numbers that most kids might accidentally pick. Instead, I'm going to actually go in and use the values inside the categories that match. So, am I male? Okay, so here are my two values, 19 and 71. And do I have pierced ears? So here are my values, 19 and 84. And do you see how I circled 19 twice? That would be the number that kids would accidentally include twice because they would have done 90 and 103. And so that's going to give you an additional 19 values. I don't want that. I only want 19, 71, and 84. Or you could have seen it as 90 plus 84. Or you could have seen it as 103 plus 71. No matter how you see it, you're not counting values twice. That's the biggest mistake that kids make there. So we end up with the probability that I could either be male or have pierced ears is 174 out of 178. That probability is much higher because it's an or statement, so you have more likelihood to, be in either category or both. So moving on, we can't use the addition rule for mutually exclusive events unless the events have no outcomes in common. So how would I know what's the easiest way to determine this? Well, that would be create a Venn diagram. It's as simple as that. So here's a silly little Venn diagram about dads, dogs, kids, and all the things they have together, hoping for hot dogs for dinner. I thought this was a cute little Venn diagram. But anyway, here is our Venn diagram regarding our males and our pierced ears. And so here's our sample space in the green. And we're going to see this Venn diagram multiple times, but they're just kind of breaking it up for us. So outcomes in the middle are double counted. And so that's the one we don't want to accidentally use these values more than once. So we want to be real cautious about that 19 in the center. These are the people who have just pierced ears. So here's event B and here's event A. These are just the males. And this would be the males with pierced ears. And any number outside would be our complement. And so in our particular example, that would be females who don't have pierced ears, right? Females who don't have pierced ears would be the only thing we haven't accounted for, and that would be that complement space, and that's that orange peachy color that I colored in. So a general addition rule for the two events. So if A and B are any two events resulting from some chance process, then P of A or B must be event A plus event B minus the two double counted, so the two events together. Okay, and so that would be how you deal with this two events where you have something or the other. You have them mutually exclusive. So this is exclusive. This is exclusive. They don't interact with each other. Okay, so because Venn diagrams have other branches, we have those specific vocab. I've mentioned them a few different times, complement and mutually exclusive or disjointed. And so let's actually see what that looks like one more time. The complement this is your notation for complement. So when you see this, that's what it means. It means you're dealing with the outcomes that aren't the event. And you can see it's physically the space outside of the circle. It cannot even exist inside the circle. And then the second concept is that mutually exclusive or disjointed. And here you can see they don't even share a space. And so here's our sample space. Here's A, here's B. They never share anything in common. Okay. And so let's move on to understanding the U and the upside down U. And so this would be union and intersection. They have a little way to remember it at the bottom of this slide coming up, but U for union, and if you see this as an N, so you can remember this for N for intersection. So that's kind of what they're going to tell you. So the intersection of events A and B would be anything that occurs that are occurring in A and in B together. So that's this portion right here. You guys recognize it in the Venn diagram as the overlap, and we call that the intersection. Remember, N for intersection. N looks like an upside down U. And then for union, this would be all outcomes. So, if I had A was 1, 2, 3, and 4, and B was 2, 4, 6, and 8. And so then my intersection of these, so A intersects B, would be 2 and 4. And then A union B would be 1, 2, 3, 4, 6, and 8. So it's just kind of a more numeric representation of this concept. Here is that hint again. Remember to keep your symbols straight, U for union, N for intersection. And I think this is our last slide, but let's wrap up Venn diagrams and probability. And so this is that pierced ears concept again. And so here is my Venn diagram, and let's read through each of these numbers and look at it in terms of our U for union and N for intersection. So here I've got this, and so the green would be our our intersection of A and B. That makes sense, right? It's where both must occur. But what if I just want the number 71? Would I just say that's A? Not quite. It's going to be A with intersecting B's complement, so outside circle B. So it wants to know because A wouldn't just be 71 because A was males and A is actually 90. So to get this number 71, you have to do 90 minus your pierced ear number. So what are we doing? Male and no pierced ears. Okay, so you would do 90 minus your value to get this number 71. Sorry, I had to look right here. So that would be A intersection B complement. But what if I wanted to know the female side with pierced ears? So that would be B intersection A complement. And so again, where did this 84 number come from? It's doing some math to separate out those values. And finally, if I want this number right here, this would be my A complement joined with my B complement, and the only number left would be 4. So this is our two-way table. Here's our Venn diagram, and this is how we write it in notation. They all mean the same thing. And finally, to summarize, okay, now are you able to describe probability models for a chance process? So, can you write an event? Can you determine if these are mutually exclusive, et cetera, et cetera? All those kinds of things would help us with our probability models. And, for the most part, can you say, if I flip a coin 25 times and it's heads 14 and tails 11 times, then what's the probability of heads? Can you describe a probability model? More than likely you can. Can you use your probability rule? So this one's a little bit tougher. It comes through more practice, which we will do in class today. So this will be can you, use your complement? Can you use your mutually exclusive? Can you use unions? Can you use intersections? Can you interpret two-way tables and Venn diagrams? And can you, again, calculate those probabilities using your complement, your mutually exclusive, addition rules, et cetera, et cetera. And so that's kind of what we did today. Hopefully you get some practice in, and then we'll do section 5.3 and dealing with independent events tomorrow.